Hey everyone. So in this video, I'm going to spend a few minutes talking about ways you can kind of approach angular impulse problems. Generally speaking, what they're going to do is they're going to ask you about what values you might need in order to calculate, drop my pen, the angular impulse for a given scenario. They might even word it, find the value to help you find the change in angular momentum. Well, change in angular momentum is just the angular impulse, right? That's the definition. So I can't go through every possible scenario because they could ask you for a variety of different things, but I can give you some kind of tricks and tips on how to approach a given problem. So for those kinds of problems where they tell you something about the given problem, you might start with your equation for angular impulse. The change in angular momentum equals torque times the amount of time that torque was applied. Okay. Well, we know that angular momentum is rotational inertia times angular velocity. So any change in any one of these will change your angular momentum. So maybe you could use one of these to solve for one of these things. Okay. We also know that torque is your force times your moment arm times the sine of the angle between the two of them. Okay, so let's say, for example, they give you a problem and it tells you that the rotational inertia is just I, and then it starts at a rotational velocity of 0, starts at rest, right? Well, what might you need in order to find your change in angular momentum if they don't give you a torque or a time? Well, you would need your final angular velocity, right? If this is constant and this changes, you just multiply the two together, you have your change in angular momentum. Another way is, what if they gave you time and they wanted to know about angular momentum change, angular impulse? Well, you just need a torque, right? See how this kind of just all plays in? Or they give you torque and you want to know, how does the change in time affect your change in angular momentum? Well, just kind of go through here, right? So this is going to be your friend. And then you can substitute each of these things in here for that. Okay, now, another way they can ask you about angular impulse is through a graph. Okay, they might do something like this. I'm just going to make a very generic graph here. Okay, so on the y-axis is our torque, and on the x-axis is the time. Okay, now from time equals 0 to whatever this time is here, how would you find your angular impulse? Well, just find the area under the curve, right? Finding the area under the curve would give you your torque times your time. Torque times time is your change in angular momentum. Now, it's very important that you find the area because of this section right here, right? This section right here, okay? Here, the torque is not constant from time 0 to whatever time we're going to call this. Because it's not constant, you can't just multiply whatever value this is here by the time here, right? That's not all of that space. It changed. In order to get that change, you need to find the area under that curve. Okay, if it's constant like this, yeah, it's just pretty much a straight multiplication because the area of a rectangle is base times height. Okay, so that's kind of a way you can approach that one. Honestly, for angular impulse questions, it's all about just being able to look at the equation, see what they've given you, and try to work out what you might need in order to solve for it. On the rare shot, you'll get a problem that has some math involved. Maybe they've given you multiple forces and you've got to use those forces to find the net torque and then a time, right? There's all different ways you can do that. So let's take this for example. going to get one problem here. So we've got a circle here. It's a disc attached frictionlessly to a horizontal surface, and I'm going to apply a force right here at its radius, okay, along the tangent. Okay, what might I need to do in order to calculate any change in angular momentum? Well, we know that the rotational inertia, the I, is going to remain constant because I'm applying the force out here. This object is not changing its mass or how that mass is distributed, so I is constant. Okay, what could I change? Well, let's see. If I kept a constant torque, then what would matter is the amount of time that that force is applied, because your torque times time is your change in angular momentum. Okay, so that's just another quick example there. I don't really have much else to add to that. Really, I would just say make sure that you've got your delta L equals torque times your time, and any equations that you can substitute in one for the other will work just as fine. Okay, so with that, I'll leave you to it. Till next time.